Hi, I'm Rob, and welcome to this, our 13th lesson on the topic of trigonometry. And what we're going to do in this lesson is we're going to combine some of the stuff that we've done over the last couple of lessons working with arcs and sectors to solve some compound problems and look at some real-world applications involving parts of a circle. So I'm going to begin on page 154 of the notes. And the question on page 154 looks like this. And you can see it says an underground traffic tunnel has a circular cross section. Okay, we're dealing with a circle here. And it says O is the center. So this point here, O is the center of the circle. Okay, so O is the center of the circle. And it says the angle marked theta in the diagram is 143. So this angle in here is 143 degrees. Okay, it says the internal radius of the tunnel is 7.8. So remember, because this here goes from the center out to the edge, that's 7.8 there, and so is this one here. So they're both 7.8, and the first thing we have to do is to find x, the width of the road. So again, what I've done there is I've filled in the relevant information on the diagram. So we've got the angle of 143 and the two 7.8s, right? So what that means is we've got a diagram that looks like this. So that's 143, these are both 7.8, and I'm asked to find this width here, x. So notice that side there, x, is just part of this triangle here. I'm trying to find a side in a triangle, and we've done a lot of work on that over the previous lessons, how to find a missing side. You'll notice in the case of this one here, the triangle's not right-angled, okay? So I'm picking between my sine and cosine rules, and I can't use my sine rule because I don't know a pairing. I know this side but not the angle, this side but not the angle, this angle but not the side. Or do I? So at first glance, you're kind of saying, well, look, that looks like a cosine rule. But what you might notice here as well is that because that's 7.8 and so is that, it means, in fact, that this triangle here is isosceles. These two sides are the same length, right? Which means if those two sides are the same length, it means that these two base angles here match as well. So if I subtract 143 from 180 and divide my answer by 2, I can find that that angle there is 18.5, and so is that one, because the triangles are isosceles. And if I spot that, it means I do in fact have a pair, 7.8 and the angle of 18.5 degrees, so I could use my sine rule. So it is possible to use your sine rule there if you spot the triangle as isosceles and that you therefore know what these two angles here are. If you don't spot that, we can just go ahead and use the cosine rule. So when you're using your cosine rule, a squared equals b squared plus c squared minus 2bc cosine A. Remember, the side that goes by itself on the left-hand side here is the one that's opposite the angle. And in this case here, that's going to be the x. Okay, so we get x squared is equal to 7.8 squared plus 7.8 squared minus 2 times 7.8 times 7.8 times cosine 143 degrees. And if I put that entire left-hand side there, or sorry, that right-hand side into my calculator and push a few buttons, it's about 218.86. Again, I'll keep the entire number on my calculator display screen, and then just take the square root of that to get your answer. The square root of 218.86 comes out at, it says to give your answer to one decimal place, that's 14.8. And remember, it's a real world problem, so your answer of units. So because we were told in the question that the radius of the tunnel is 7.8 meters, my answer would have the same units as 14.8 meters. Okay, so that's just a straight cosine rule or a sine rule. As we said, you normally have options in a question of this type. It's up to you. So part 2 then, on the next page, it says find y, the height of the road surface above the bottom of the circle. Now you can see on the diagram that y is marked in here. So this is y here. That blue line there, that's y. So the question is, how am I going to find that? Well, if I'm looking at that diagram, what I'm thinking is I'm going to use my triangle up here to find this. To find the red line there, all right? And then because the thing that I need to spot in my own head here is that the red and blue lines together, this line here, from there all the way down, is 7.8. Because it's another radius, isn't it? It's going from the center of the circle to the edge. So the red and blue lines here together make up 7.8. So if I can find that red line there from the triangle on top and subtract it from 7.8, I think I've got the blue line at the bottom. Now that might take a minute or two to spot, but that's fine. Okay, remember that when you start a problem of this kind, there's going to be a lot of thinking at the beginning, chewing your pens and trying to spot this. And once I spot it, the calculation should happen quite quickly. So it's all about trying to find that red line there. I'll just call that H, the height of the triangle on top. Okay? Now, there's a couple of ways of doing this. One way I could do this, obviously, is you can see that because I'm dropping, that's a vertical line there. Because when you talk about the height of something, it's the vertical line. So that's a right angle there. Okay, the line we're dealing with here is vertical because that's what height means, the vertical height of the road, right? That's a vertical line, and that's the horizontal road surface, so that's a right angle there. So I could work with this triangle here. Because as we said a moment ago, I know that this triangle, this angle down here is 18.5, because the triangle is isosceles. So you've got 18.5, you know this side here, and you want to find the red one. You can use normal right angle triangle trigonometry, right? That's perfectly fine. Okay, it's not the only way to do it, it's just one way of doing it. You could use your sine rule, all right? But in this case here, there's another way to think about this. And just, again, to illustrate something a little bit different, rather than using the same method to solve a triangle all the time. Notice here that for this triangle here, the triangle on top, all right, I can find the area of that triangle, as we did in a previous lesson. Okay, to get the area of that triangle. And notice, because I've got these two sides, and the angle in between them, the included angle, I can use a half AB sine C to get the area. So if I do that, just bear with me on this, we'll have a look at that. So the area of the triangle is going to be a half AB, for the two sides, 7.8 by 7.8, times the sine of the angle in between them, sine 143. Okay, and if I do that calculation, it comes out about 18.3 meters squared. Right, so that's the area of that triangle there, the top triangle. But notice, there's another way I could get the area of the triangle, right? Couldn't I also get the area of that triangle? It's a half the base by the perpendicular height. And I just found what the base was in part one. Part one of the question was to find that base there, the side marked x, which is 14.8. So I can also get the area of that triangle by saying, look, it's half the base by the height. So the area is a half the base, which is 14.8, times the height, which is h. This height here, and I know the answer that should give me is 18.3. So it's just kind of finding the area of the triangle two different ways, and obviously the area has to be the same whichever way you choose to calculate. You can see there's a very simple equation to solve to find h. Okay, that a half of 14.8, that's 7.4 h is equal to 18.3, and I'll divide across by 7.4 to the h by itself. So 18.3 divided by 7.4 is about 2.5 meters. All right, it's the very same answer you would have got if you'd solved that triangle there. Again, as I said, problems of this kind, there's always multiple solutions. So you're not looking for the correct way of solving it, you're looking for a correct way of solving it. So h is 2.5, and then don't be the guy who forgets that that's not the answer to the question. Okay, what that means, the little red line here is 2.5. We're trying to find the blue line, the height of the road above the base of the circle. So those two together make up a radius. Because that line there goes from the center O out to the edge, that's a radius, that's 7.8. So the height for y is 7.8, take away 2.5, which is 5.3 meters, and that's my answer to part two. Okay, so the height of the road above the bottom of the circle is 5.3 meters. Now, the last part of the question, part three, it says the shaded area in the diagram represents concrete added to the bottom of the cylindrical tunnel to form the road surface. So this shaded area here is the concrete, right? It says, if the tunnel is 1.32 kilometers long, find the volume of concrete required. So I'm hoping that if I remove this part of the diagram here, if I just remove this around here, that might look a bit familiar. That's something we met in the previous lesson. There's your segment of a circle, right? Because remember, that's the center of the circle there, and these are both radii. So this shape here, that's a pizza slice, that's a sector of a circle, and we have a formula for getting the area of the sector. That's a triangle here, and we already know what the area of the triangle is. We found that already. And sector, take away triangle will give you the segment. So that's the way to do this one here. So I'm going to find that shaded area there because it's the area of a segment. And that segment calculation, as we said in the previous lesson, is well worth having in your back pocket, having in your toolkit. All right? So if I get the area of the sector, first of all, so remember, you've got two formulas to get the area of a sector, depending on whether the angle at the center is measured in degrees or radians. This is degrees, so we use the degree version, which remember is theta over 360. So it's 143 over 360 multiplied by pi r squared. Okay, so it's pi times 7.8 squared. So there's the angle of the center, there's the radius. And if I put that into my calculator, that comes out at about 75.9 meters squared. Okay, so that's the entire pizza slice here, this entire shape, right? That's a bit, if you ignore that line there, that's your sector there, and the area of that is 75.9. The triangle we know already, okay, because we calculated that back in part 2. The way I chose to do part 2, that's 18.3 meters squared. So your segment then is just one minus the other. So the segment is 75.9, take away 18.3, which is 57.6 meters squared. Right, now that's the area of this part here, right? Now, that's not what the question asked me. It asked me for the volume of concrete required. So to get the volume of a shape like this is a shape of uniform cross-section. All right, so no matter where you slice through the tunnel, if you go to any point of the tunnel and slice through it, the shape will look exactly like that. It doesn't get narrower or wide the further back you go, right? So in other words, the concrete is this shape here going all the way back. All right, so if you can imagine that shape there going all the way back, that's the concrete in the tunnel. So to get the volume of a three-dimensional shape like that, you just multiply the area of the front by how far back it goes. Like any other prism, any other three-dimensional shape like that. So you get the area of the front multiplied by how far back the shape goes. So we know the area of the front is this, and how far back does it go? 1.32 kilometers. So if I multiply those two together, I've got the volume of concrete required. The one thing to be careful of here is to watch your units, that's in meters squared, and the length of the tunnel is given in kilometers. So don't just multiply that by 1.32, your units don't match. Either convert that into kilometers squared, or what's easier, convert the length of the tunnel into meters. It's always easier to convert length than it is area, all right? Because remember, there's 1,000 meters in a kilometer. There aren't 1,000 meters squared in a kilometer squared, right? So remember, so 1,000 meters is 1 kilometer, okay? But if I want to work out what 1 kilometer squared is, well, that's 1 kilometer by 1 kilometer, which is 1,000 meters by 1,000 meters, which is 1,000,000 meters squared. So it's not as straightforward to convert area as it is to convert length. So in a question of this type, rather than trying to turn the area of this shape here into kilometers squared, I'll turn the length of the tunnel into meters. Okay, so 1.32 kilometers, okay, remember, is the same as 1320 meters multiplied by 1,000. You convert kilometers into meters, then we multiply those two together. So it's 57.6. The area of the front multiplied by the length of the shape, 1320, and that comes out as 76032 meters cubed, and that's the volume of concrete required. Okay, that's a nice question there, bringing in that segment calculation. So if we then look at the question on the next page, on page 156, question 13.2, this one's adapted from an NCCA 2010 mock paper. So you can see what the question says. It says, arched wonder buildings do not need any support inside due part to the fact that the shape is an arc of a circle. Okay, so it's an arc of a circle. It says the arc cannot be more than a semicircle. Okay, so the arc, it can't be more than a semicircle. And the span of the building is the total width from one side to the other. So in this case, this diagram here, that's the span. It's that distance across there from one side to the other. The span of this one here is 90. So in part 1, it says the span for such a building is 90 meters and the height is 25 as shown below. Find the radius of the arc. Now, the key thing here to point out to begin with is that that point down there is not the center. It couldn't be, if you think about it, because if that was the center there, wouldn't that mean that this is a radius here, going from the center to the edge, so is this, and so is this. And they would all have to be the same length, and they're not. You can see they couldn't be the same length here, all right? Because the case of this one here, this one here is going to be what, 45? And this one here is going to be 45. Because they're both half of the 90 down here, because the height's right, the shape is symmetrical, and this one's only 25. So if that was the center down there of this shape, it means that all three of those measurements are the same. If this was 45 as well, it would mean that this shape was a semicircle, and it'd be very easy to find the area, and the radius would be 45, but it's not. So in the case of this one here, the radius is down here somewhere. So if you can imagine, in the case of this particular shape, that the radius is down, the center of the circle is down here somewhere. Like that. Right? So this here, this radius here, this radius here, and this radius here are all the same length. So that's the center point we're dealing with down here. We're trying to find that. So in this case here, because this shape is less than half a circle, okay, it's less than a semicircle, which the question says it has to be, okay, the center point I'm looking for is down here somewhere. So if you look at the at the diagram here, you can see that if we drop a line at this, because remember height again means vertical. And when we talk about the height of something, we're talking about a vertical line, vertical height. Okay, so if I drop a vertical line down here like this, all right, this part here, that bit is 25, given the question. And then these two bits on the bottom here are both 45. So that's 45 there. And so is that to give me the 90 meter radius in total. Okay, so the triangle I'm going to work with here, not the only way to do it, but the triangle I'm going to work with here is this one. And you notice if I was to turn this diagram upside down, it's the same diagram we had in the tunnel question a moment ago, right? So there's your the road there. There's your 1, 4, 3. There's 7 points. It's the same question. Just the information I'm given is different. I'm trying to find something different here. In the previous question, I knew what this here was. Okay, in this case, I'm trying to find, so that's the radius there. And remember, because that's a vertical height there, and that's the horizontal span of the building, that's a right angle there. So these angles here are right angles. So what I'm going to do in this question, I'm going to work with that triangle there. And that might not be easy to spot. Again, remember, the question of this type, when you're dealing with a real world problem, you'll probably spend a lot of your time trying to spot the triangle you're going to work with, rather than getting stuck in straight away. But notice it's a right angle triangle, and I know 2 of the sides. So if I can find the third side, I can maybe use Pythagoras. So now my question becomes, what's this bit here? Okay, and if you think about that, you might kind of arrive at the answer there. If you have a look at the diagram, it might not be obvious, but again, giving yourself a bit of thinking time there, you might spot that. Now remember, from here to the top, that's a full radius there. That's OR. So whatever OR is, that's OR there. This bit's 25. So that bit there is OR minus 25. It's a full radius, take away the 25 up there. So now, what I'll do is I'll apply Pythagoras' theorem to that triangle. So remember, there's the right angle, the side opposite the right angle, that's OR here. So we get OR squared is equal to 45 squared plus OR minus 25 squared. There's Pythagoras. You can see there's an equation that contains OR, which I can now solve to find the value of OR. Okay, so that's going to just give me OR squared there. 45 squared is 2025. And if I square that bracket, remember that's just algebra like that. It's just OR minus 25 multiplied by itself. So OR minus 25 by OR minus 25. And if you do that squaring out, you get OR squared minus 50 OR plus 625. And notice this things just keep getting better. All right, everything's coming up us because the OR squareds on both sides will cancel. If I subtract OR squared from both sides, there's no OR squareds. So you can see if I add 50 OR to both sides to bring that across here, I get 50 OR over on the left-hand side. And 2025 plus 625 is 2650. And then divide across by 50, OR is equal to 53. And that's my value for OR. So OR there is 53 meters. Okay, nice question, that one. So if you look then at part 2 of the question, same kind of idea. So again, it's all about kind of interpreting the information here to begin with. So the way this part of the question reads, it says, an Air Force needs a wonder building to house a Tornado military jet. The dimensions of the jet are as follows. The wingspan is 40 meters. So the wingspan is obviously from the tip from here to here. from the tip of one wing to the other, that's 14 meters. The height up, from the ground up as far as here is 6 meters. And the height of the wingtips above the ground, that distance there is 2 meters. Okay, that's given there. It says the shelter must be at least 0.5 meters above the top of the tail and at least 1 meter clear of the horizontal wingtips. Horizontally the wingtips. So it says for the shelter to have the exact clearance required, find the radius of the arc. So it's the same question we had a moment ago, just have to kind of work out the measurements myself. They're not given here, right? Now, notice here that that what you might be doing when you begin with is you might be kind of saying, well, look, here's the span I'm going to work with in this case is this. That span there. The problem is I'm not sure what that span is. I'm not given any measurements along the ground there. I'd be guessing. I'd be using the grid lines maybe to guess my answer there. I wouldn't be as confident. But look what I do know. So I know the wingspan is 40 meters. So on the diagram, that goes from here across to here. See it? So there's the 14-meter wingspan, right? And it says that the shelter has to be at least 1 meter clear horizontally of the wingtips. So we need 1 meter on this end, which is marked in the diagram, and 1 meter on that end. So what that means is that entire line there is 16 meters. So the red line across here is 60 meters. The wingtip, the wingspan of the jet, plus a meter clearance on either side. Okay, so that's, if you like, the measurement that was like the 90 in the previous question. Okay, that's the span of the shape I'm going to deal with. Right? So what I now want is this height here. Because again, in my head, the shape I'm dealing with, the center point is probably down here somewhere. Right? Like we had in the previous question, the center point is down here. I'm going to make this little right angle triangle here like this. I'm going to work with this triangle here. So I know that this bit here, okay, because the entire width is 16, that bit there is 8. I know that this bit over here is or. All right, so the question is, what's this bit here so I can use Pythagoras? And to do that, I like that again, I just want to find what the blue line is there and subtract that from or to get my answer. Okay, so notice we're told that the height of the jet is 6 meters. So from here to the top of the tail there, that's 6 meters. And then we must have another ½ meter above that, so because we've got a ½ meter above here. So from here all the way down to the bottom, to the ground of the shape, is 6.5 meters. But because the wingtips, the red line here, are 2 meters above the ground, if I subtract 2, it means that that's 4.5 meters there. Now, the reason I'm thinking about using those measurements there, if I tried to use the span along the ground here, I wouldn't be using that piece of information there or that one. And I'd be very skeptical about kind of doing a question when some of the measurements I've been provided with I'm not given. So I think that's 4.5 there. The entire height is 6.5, the height of the jet plus the 0.5 meter clearance. And the span is 16, which means the half of it there is 8. So now I've got a triangle I can solve. So that gives us a diagram that looks like this. All right, same as we had in the previous question. This bit here is 8 meters. It's half the span of the shape we're looking for. If this bit here is 4.5, then this bit down here is or minus 4.5, and that's or. So again, I'll just apply Pythagoras' theorem. It should be the same as the previous calculation now, no problem. Or minus 4.5 squared like that. So or squared is equal to 64. And you square that bracket out, you get or squared minus 9 or plus 20.25. Okay, and again, subtract or squared from both sides, they cancel. I move the 9 or across onto the left, it becomes positive. So I get 9 or like that is equal to 84.25. And then divide both sides by by 9, we get that or is about 9.36 meters. And noticing, again, you know, I could now, once I've got the radius, I could now find that area if the question demanded it. Like if I wanted to find the volume of a building, I could do it that way once I've done the calculation. The key thing there is being able to find or. So the last question then to bring us up to the end of this lesson is this one here from page 158. It says a chain runs around 2 sprockets as shown in the diagram below. The smaller sprocket has center P, so that's the center point there, and a radius of 67 millimeters. So this radius here is 67, the radius of the smaller sprocket. The large sprocket has center Q, that's this point here, okay, and the radius is 135. So the radius of the larger sprocket there is 135. And it says the distance between the two centers, P and Q, is 293. So you can see that this line here, between P and Q, that line there is 293. Okay, so that's the information we're given. And it says, given that POR is drawn parallel to AB. So this dotted line here, POR, is parallel to that one. Now notice that these two right angles are marked here and here. Okay, that the alternative way to think about that is that, remember, that line there, that line segment AB is a tangent to both circles. And an important piece of information to have in my back pocket when I'm solving any kind of trigonometric problem like this is that a radius and a tangent are always perpendicular at the point of contact. Okay, so that would have been a right angle anyway. Because AB is a tangent, only hitting the circle once, it means that it's perpendicular to the radius at that point. So that's a right angle up there. But because the dotted line down here is parallel to AB, it means these are right angles here as well. Okay, so that means the shape APOB is a rectangle. So this guy here, that shape going down there, cross, up here, like that, that's a rectangle. And there's a right angle here, so this guy here is a right angle triangle. So the final thing to notice there before we kind of get stuck into solving it, okay, is that because this shape here is a rectangle, if that side is 67, then so is this. Opposite sides of a rectangle are the same length, that's 67. And then because the entire radius BQ, this entire radius here, is 135, if I subtract 67 from 135, I get that this bit out here is 68. All right, so that's the shape I'm dealing with here. All right, so look at this triangle here now. It's a right angle triangle. I know this side here and I know this side here. I can find the third side there, POR. So in this diagram here, there's the 293, there's the 68, okay, and there's the side I'm going to find here. I'm going to find that side there, POR. Let me just call that X. So I can use Pythagoras theorem. It's a right angle triangle. I know two of the sides. I can find the third one. And the hypotenuse here is the 293. That's the one that's opposite the right angle. Okay? So what that looked like is 293 squared is equal to x squared plus 68 squared. So 293 squared minus 68 squared is equal to x squared. And then just take the square root of both sides to give me my value for x. And that comes out at exactly 285. And again, be careful. Practical question, my answer has units. It's 285 millimeters, right? Now, just notice then in part 2 on the next page, it says find the angle APC. And the angle APC is that angle out there, okay? The angle APC, right? Correct the nearest degree, the angle APC. Now, actually, the angle APC, it could be this one in here, but it doesn't really matter. I can find either one of them the same way. Okay, normally we'd try and mark the angle there to make sure you know which angle APC, but either one of them will lead me to the solution I'm aiming for in the last part of the question. So in order to find that angle there, notice that that's a right angle there, because as we've already established, this bit here is a rectangle. If I can find this bit here, okay, I can add those two together to get that angle there, and it might or might not be obvious that this angle here will match it. So this angle here and this angle here are the very same because the shape is symmetrical. So it's about finding this little angle down here. Notice that's easy to do because it's a right angle triangle. So if that's a right angle triangle there, this side here is the opposite. So 68 is the opposite here. It's opposite the angle I'm looking for, okay? The 293, that's the hypotenuse. So opposite hypotenuse means sine. I can just use the sine the sine ratio to get my answer. It's quite quick, all right? So it'll be that the sine of the angle we're looking for here, and the angle I'm trying to find there is the angle of what? OR-PQ. So it goes from OR to P to Q. So the sine of the angle OR-PQ, I'll just call it, maybe call it theta. Okay, call it angle theta. So the sine of theta is equal to opposite over hypotenuse, just 68 over 293. So theta then is the inverse sine of 68 over 293. And that comes out, it's round about 13.4. It's 30 degrees, so we call that 13 degrees. right? So what that means now is that this angle here is 30 degrees and that angle there is 90. So that angle there is 103. Okay, it's 90 plus 30, that's 103 there. And then so is this one here. So that larger angle there is 103 plus 103, which is 206, right? So that large angle there is 206, and it means the one on the outside here, the angle APC, which is actually the one that I'm looking for. You'll see why we get to it in a moment. It's 360, take away 206, which is 154 degrees. So this one here is 206, that one there is 154. Because the question doesn't specify which angle APC you're looking for, either of those are correct, but it's actually this one out here I'm going to need for the last part of the question. So it doesn't matter which one of those I gave as my answer for that part of the question. Now, the third part, to find the angle BQD, again, that's the same out here. That's this one here, or if you like, it's that one there. From B to Q to D, right? So it's that angle there we're dealing with here. Now, what might or might not be obvious to you, and if this is not obvious and you go ahead and do some calculations, you'll find you get the same answer either way. That because these two lines here are parallel, they're both perpendicular to that top line AB. And these two lines are parallel for the same reason. It means the angle formed here and the angle formed here are corresponding. They'll be the same. And the angle out here and the angle out here will be the same. So I'm fairly sure that that angle there is 206 degrees, just like this one here was. The same way that angle there was. Those two angles will match. So this angle here and this angle here are the same size. Because those two lines and those two lines are parallel. So these two lines are parallel and so are those two, all right? And the angle on the other side is going to be 154 in both cases. Because now, in the last part of the question, part 4, it says find the total length of the chain that runs around the two sprockets, correct the nearest millimeter. So we want to find the length of the chain that goes all the way around from here back to where we started from. So notice what I know already. I already know what this is, right? That side there is 285. Now I should have mentioned back when we were doing part 1, right? That when we were doing part 1, we found X, this side here, and we said that was 285. I should have included a line at the end there that says that means that the side we were looking for, that AB is also 285. Because the X I found there was not the side he asked me to find. He asked me to find AB. But remember, because these two guys here are both opposite sides of a rectangle, that means they're the same length. So this here and this here are opposite sides of a rectangle. So if this is 285, so is that. And if you're asking yourself in an exam, should I explain that to the examiner? Should I tell the examiner why AB is 285 as well? Or can I just write it down? In an exam, the moment that question enters my head, should I tell the examiner or should I not? I would anyway, just to cover myself. Because that way, if the examiner needs to know how I know that, I've told him. If he doesn't need it, he can ignore it anyway. So I would just maybe mention there, because they're opposite sides, okay, of a rectangle. Right, just so the examiner knows I'm not pulling that out of fresh air, okay? But in reality here, once I get that AB is 285, that's fine. So AB is 285. And again, it might or might not be obvious that that's 285 as well, right? Because this shape here, so that shape there and this one are identical. All the measurements the same. That might be obvious, it might not be. Might be worth taking a second to convince yourself of that, but they are the same. So I've got those two. So the only two bits I need now to make up the entire chain are this bit out here, right, that piece, right, and this piece here. Those four added together will make up the total length of the chain. And the two red lines I've marked in there, they're both arcs. Right? They're both curved lines, arcs of a circle there. And again, we have formulas for finding the length of those. And to find the length of an arc, all I got to do, remember, are the two measurements I need the angle at the center and I need the radius. So for this one here, the radius is 67. And the angle, remember, is the 154, the smaller angle. So if I want to find that one, that arc there, okay, it's going to be, again, we're going to use the version of the length of an arc formula where the angles are in degrees. So it's 154 over 360 multiplied by 2 pi or. So 2 pi and then or is 67. So if I pop that into my calculator and push a couple of buttons, that's about 180 millimeters. It says the nearest millimeter, so I'll just give that one, it's 180. It's like 180.08. That's about 180 millimeters. That's this one here, right? So this one out here is 180. So to find the longer one then, to finish it up, again, that arc on the other end, well, for this one, the radius is 135. It's the bigger radius. And the angle is the one on the outside here, is the 206. Is the angle there. So I actually needed both of those, the 154 and the 206 anyway. So that one's going to be 206 over 360 multiplied by 2 pi or 2 pi times 135. And if I put that into my calculator and push a few buttons, that one comes out at about 485. Right? So now the total length then is just the 4 of those added together. It's the 180 plus 285. So it's 180 plus 285 plus this one here, which is 485, plus another 285 to be back where I started from. And if I add all those together, it's 1235 millimeters. And that's my answer. Good question. So there's 3 nice examples of real-world problems involving working with arcs and sectors. That little calculation involving segments is one that's well worth having in your back pocket. So in the next lesson, what we're going to do is we're going to move towards having a look at working with trigonometric graphs and functions. That's where we're going to go next.